to Part 1, Caching Overview. Earlier, the course mentioned the move from monolithic applications toward modern microservice-based applications. Modern applications continue to evolve in scope and complexity, and the demands on the infrastructure for performance and scale only go in one direction, up. Applications have evolved from single-server applications with hundreds of users to distributed global applications that millions use. All those users send requests and expect immediate responses. Think about the data expectations for applications that use Internet of Things, also known as IoT, devices in the field to send millions of requests. As another example, consider the data necessary for a bidding website, where a few hundred microseconds would be meaningful to the outcome. Still, another example is a massive global online game, where users interact with the game and each other, which would be quite data intensive. Developers must rethink how they store and access data to meet these performance demands, and how to support the scale and reach of modern applications. Caching is one strategy to address these challenges. Caching is serving requests from a copy of data rather than making the request to the original data source. The cache is the copy of the data, and the original data source is called the origin. The cache is a high-speed data storage layer, and it stores data transiently. Data in the cache has a time to live, or TTL, so the data in the cache doesn't get stale. A cache's primary purpose is to increase the performance of data retrieval by reducing the need to access the origin. The performance increase can come from faster responses back to the client, reduced load on downstream services and resources, or both. In the Amazon API Gateway module, you learned about an example of caching. When you turn the cache on in API Gateway, the service checks the cache first to see whether the requested data exists there. If it does, then API Gateway returns the response from the cache without needing to go to the backend data storage layer. This process can reduce the latency of responding to the request and the number of calls that reach your backend services. You can apply caches and use them throughout various layers of technology to improve performance. Accelerate retrieval of web content on the client side by using HTTP cache control headers. To accelerate retrieval of web content from web servers and manage web sessions on the server side, you can use CloudFront, ElastiCache for Redis, ElastiCache for Memcache, and AWS partner solutions. To accelerate application performance and data access, use ElastiCache for Redis, ElastiCache for Memcache, and AWS partner solutions. And reduce latency associated with database query requests by using ElastiCache for Redis and ElastiCache for Memcache. In this module, you will learn about ElastiCache and CloudFront. However, you might use other caching options at different layers of your application, depending on the specific performance requirements and data that your application needs. That's it for this video. Thanks for watching. I'll see you in the next one. Section 2, Part 2, Caching Overview. Caching can benefit both read-heavy and computer-intense workloads. Read-heavy application workload benefits include reduced latency and improved input-output operations per second, also known as IOPS. Examples of read-heavy applications include social networking, gaming, media sharing, and question and answer portals. Compute-intensive workloads manipulate datasets. Examples include recommendation engines and high-performance computing, also known as HPC, simulations. In these applications, large datasets must be accessed in real time across clusters of machines, which can span hundreds of nodes. Due to the speed of the underlying hardware, manipulating this data in a disk-based store is a significant bottleneck for these applications. Based on application requirements, developers choose strategies for how often to refresh the cache and which origin of data to cache. When deciding what data to cache, consider these factors. Speed and expense. It's generally slower and more expensive to acquire data from a database than from a cache. Some database queries are inherently slower and more expensive than others. For example, queries that perform joins on multiple tables are significantly slower and more expensive than simple queries on single tables. If the data requires a slow and expensive query to acquire data, it's a candidate for caching. If acquiring the data requires a relatively quick and simple query, it still might be a candidate for caching, depending on other factors. Data and access patterns. To determine what to cache, you need to understand the data itself and its access patterns. For example, it doesn't make sense to cache data that is rapidly changing or infrequently accessed. For caching to provide meaningful benefit, the data should be relatively static and frequently accessed, such as a personal profile on a social media site. Conversely, you don't want to cache data if caching it provides no speed or cost advantage. For example, it doesn't make sense to cache web pages that return the results of a search because these queries and results are almost always unique. Staleness. By definition, cached data is stale data. Even if it's not stale in certain circumstances, cached data should always be considered and treated as stale. When you determine whether your data is a candidate for caching, you must also determine your application's tolerance for stale data. Your application might be able to tolerate stale data in one context, but not another. For example, consider an application that serves a publicly traded stock price on a website. For this application, a short delay might be acceptable if it has a disclaimer that prices might be delayed by a specific number of minutes. But when an application must serve the stock price to a broker who is making a sale or purchase, you want real-time data. Trade-offs. Depend on your caching strategy. Caching can add complexity to your development effort. You must weigh the benefit to your workload against the effort to write code to cache data or potentially handle security for an additional vector of attack. Caching can cause additional cost, so optimizing for cost is an important part of deciding what and how to cache. As a developer, you must understand how caching might benefit your application, but be wary of optimizing too early. It is best to wait until the application is complete so you can see where the bottlenecks are. Next, monitor access patterns and performance in production-like scenarios, and then apply caching where it adds the most benefit. Here are the key takeaways for this section of the module. Modern applications put high demands on the performance of data sources in an application. Caching can improve performance by serving requests from a copy of data, a cache, rather than making the request to the origin. And caching can occur at all layers of your application. That's it for this video. Thanks for watching, and see you in the next video. This video covers Section 3, Part 1, Caching with ElastiCache. Amazon ElastiCache is an in-memory key value store that sits between your application and the data store or databases that it accesses. Caching can decrease access latency, increase throughput, and ease the load on databases and applications. Most data stores have areas of data that are frequently accessed but seldom updated. Additionally, querying a database is always slower and more expensive than locating a key in a key value pair cache. Some database queries are especially expensive to perform, such as queries that involve joins across multiple tables or queries with intensive calculations. By caching these kinds of query results, you pay the price of the query one time. Then you can quickly retrieve the data multiple times without having to rerun the query. The ElastiCache service can scale to meet demands, and it is fully compatible with the open source Redis and Memcached engines. ElastiCache supports two open source in-memory caching engines, Memcached and Redis. First, let's look at the features of ElastiCache for Memcached. Memcached offers multi-threading. With this feature, Memcached can use more CPU cores than Redis. Memcached is also designed to be relatively simple, and so it requires less maintenance than Redis. ElastiCache from Memcached also has horizontal scalability with auto-discovery, which makes it easy for clusters to add and remove nodes. This feature automatically discovers changes to the node membership in a cluster, such as new nodes that are added or nodes that were subtracted. The ElastiCache client reconfigures automatically in response. Now let's look at ElastiCache for Redis. ElastiCache for Redis supports complex data types, such as strings, hashes, lists, sets, sorted sets, and bitmaps. By contrast, Memcached is designed to cache flat strings, such as flat HTML pages or serialized JSON and objects like databases. Data in Redis has persistence, so you can actually use it as a primary data store. The Memcached engine does not support persistence. Thus, if a new empty node replaces a failed node, or you terminate or scale down a node, you lose the data in cache memory. Redis also offers high availability because you can replicate your data from the primary node to one or more read replicas for read-intensive applications. ElastiCache for Redis also has automatic failover. In certain cases, such as planned maintenance or failure of a primary node or availability zone, Redis detects and replaces the primary node. If you enabled multi-AZ deployment with automatic failover on the cluster, the role of the primary node fails over to one of the read replicas. Finally, Redis offers publish-subscribe capabilities. In this paradigm, you send a message to a specific channel without knowing exactly who receives it. Subscribers to the channel receive the message. You can use Redis to manage the channels and enable quick messaging and communications between publishers and subscribers. If you must decide which ElastiCache engine to use, Memcached is typically preferred and works well when you need the simplest model possible. However, if you need the advantages of data persistence, advanced data types, or the other features that are listed, Redis is probably your best solution. That's it for this video. Thanks for watching, and we'll see you in the next one. Video covers Section 3, Part 2, Caching with ElastiCache. Let's look at some of the terminology for ElastiCache. A node is a fixed-size chunk of secure network-attached RAM. A cluster is a logical grouping of one or more ElastiCache nodes. Each node runs an instance of the engine and version that you chose when creating the cluster. If necessary, you can scale the nodes in a cluster up or down to a different instance type. Every node within a cluster is the same instance type and runs the same cache engine. Each cache node has its own DNS name and port. Multiple types of cache nodes are supported, each with varying amounts of associated memory. Your application connects to an ElastiCache node or cluster by using a unique address that is called an endpoint. With the Memcached engine, data is partitioned across nodes in a cluster. Memcached data is partitioned across up to 20 nodes. Memcached does not have replication. The Redis engine has additional components. As new functionality was introduced into newer versions of ElastiCache for Redis to support new Redis features, some component names were modified. The console reflects the updated terminology, but to preserve backward compatibility, the API and command line interface, CLI, use the earlier terminology. A Redis shard, which is called a node group in the API and CLI, is a grouping of 1 to 6 related nodes. If a shard has more than one node, the shard supports replication. In this case, one node is the read-write primary node, and the others are read-only replica nodes. A Redis cluster, which is called a replication group in the API and CLI, is a logical grouping of one or more shards. A Redis cluster configured without cluster mode always has one shard, and this configuration has no data partitioning. A Redis cluster configured with cluster mode can have up to 500 shards, and your data is partitioned across the shards. As a developer, you don't have to worry about actively managing ElastiCache after your cluster is up and running. ElastiCache is a managed service, so it handles administrative tasks like provisioning, failure detection, and software patching on your behalf. ElastiCache integrates with other AWS services, including Amazon Elastic Compute Cloud or Amazon EC2, Amazon Relational Database Service or Amazon RDS, and Amazon DynamoDB. ElastiCache also integrates with deployment management solutions such as AWS CloudFormation, AWS Elastic Beanstalk, and AWS OpsWorks. Therefore, you can focus on the application logic and not the infrastructure. Your focus as a developer is on writing the code to handle the following logical actions. The first is to request data from the cache. If you find the data in the cache and it has not expired, which is called a cache hit, the next step is to return it to the requester. If you don't find the data you need in the cache or the cached value has expired, which is called a cache miss, go to the third step and request the data from the origin. Then return the data to the requester, and as a last step, update the cache with the data retrieved from the origin. In this example architecture, Elastic Load Balancing distributes application traffic across multiple EC2 application instances, which are making external API requests. Numerous databases reading requests for the same data increases the response time, so you can add ElastiCache to improve response times and alleviate database pressure. The application reads from the cache. If the information is not available in the cache or is expired, the application reads from the database. This could be an Amazon RDS DB instance, DynamoDB database, or another database. If the database receives numerous read requests from the same data, the application writes the data received from the store to the cache. In this way, the data can be retrieved more quickly the next time it's requested. In the example with a cache miss, 3 trips are related to the request. You must send the initial request to the cache, query the database, and then update the cache. A cache miss can noticeably delay returning data to the application. One strategy is to load all data into the cache in advance rather than a subset. You might use this strategy if your application cannot tolerate the cache miss penalty for any request. Recall that a cache miss might happen if the desired value is not in the cache or the requested key has expired, meaning the time to live or TTL has expired. In addition to deciding what to cache, you must decide the TTL for data in the cache. A short TTL might result in more cache misses, but extending the TTL could mean you're returning stale data to your application. Cache expiration can get complex quickly. In a real application, a given page or screen often caches many different kinds of data at the same time. For example, profile data, top news stories, recommendations, or comments. Note that all of these could have different update methods. One strategy is to always apply a TTL to all of your cache keys. TTL is an integer value that specifies the number of seconds until the key expires. Test with production-like data and continue to monitor caching behavior and application performance in production. This strategy optimizes your choices for what to cache and how frequently it must be refreshed. Here are the key takeaways for this section of the module. ElastiCache is a fully managed in-memory data store with sub-millisecond latency. ElastiCache supports 2 open-source in-memory caching engines, Memcached and Redis. And a node is a fixed-size chunk of secure, network-attached RAM, and a cluster is a logical grouping of 1 or more ElastiCache nodes. That's it for this video. Thanks for watching, and we'll see you in the next one. When someone browses your website or uses your application, the request is routed through many different networks to reach your origin server. The origin server stores the original definitive versions of your objects, for example, web pages, images, or media files. The number of network hops and the distance that the request must travel significantly affect the performance and responsiveness of your website. Further, network latency is different depending on geographic location, which is where a content delivery network, also known as a CDN, comes in. A content delivery network, or CDN, is a globally distributed system of caching servers. A CDN caches copies of commonly requested files, static content, such as HTML, CSS, JavaScript, and image files that the application origin server is hosting. The CDN delivers a local copy of the requested content from a cache edge or point of presence, also known as POP. The CDN uses the copy that provides the fastest delivery to the requester. CDNs also deliver dynamic content that is unique to the requester and not cacheable. Having a CDN deliver dynamic content improves application performance and scaling. The CDN establishes and maintains secure connections closer to the requester. If the CDN is on the same network as the origin, routing back to the origin to retrieve dynamic content is accelerated. Furthermore, content such as form data, images, and text can be ingested and sent back to the origin. This process takes advantage of the low latency connections and proxy behavior of the POP. Amazon CloudFront is a CDN that securely delivers data, video, applications, and APIs to customers globally with low latency and high transfer speeds. These attributes all exist within a developer-friendly environment. CloudFront integrates with AWS Shield to provide built-in security against distributed denial of service or DDoS attacks. The service also integrates with Amazon Simple Storage Service, known as Amazon S3, ELB, and Amazon EC2. You can use these services as AWS origins for your applications. CloudFront is also highly customizable. It integrates with Lambda at Edge to run custom code closer to your users and to customize the user experience. CloudFront delivers your content through a worldwide network of data centers, which are called edge locations. CloudFront edge locations are connected to AWS regions through the AWS network backbone. When a user requests content that you're serving with CloudFront, they're routed to the edge location that provides the lowest latency. In this way, the content is delivered with the best possible performance. CloudFront edge locations ensure that popular content can be served quickly to your viewers. The cache key is the unique identifier for every object in the cache, and it determines whether a viewer request results in a cache hit. A cache hit occurs when a viewer request generates the same cache key as a prior request, and the object for the cache key is in the edge location's cache and is valid. When a cache hit occurs, the object is served to the viewer from a CloudFront edge location. After you configure CloudFront to deliver your content, what happens when users request your files? First, a user assesses your website or application and requests one or more files, such as an image file and an HTML file. Then, DNS routes the request to the CloudFront POP, the edge location, that can best serve the request, typically the nearest CloudFront POP with the lowest latency. When CloudFront receives the request, the service first checks the edge location's cache for the requested files. If the files are in the cache, CloudFront returns them to the user. If the files are not in the cache, CloudFront compares the request with specifications in your distribution and forwards the request to your origin server for the corresponding file type. For example, it would forward the request to your S3 bucket for image files and to your HTTP server for HTML files. The origin server sends the files back to the edge location. Then, as soon as the first byte arrives from the origin, CloudFront begins to forward the files to the user. CloudFront also adds the files to the cache in the edge location for the next time someone requests those files. CloudFront also has regional edge caches, which bring more of your content closer to your viewers. Regional edge caches include content even when it's not popular enough to stay at a POP, to help improve performance. Regional edge caches help with all types of content, particularly content that tends to become less popular over time. Examples include user-generated content, such as video, photos, or artwork, and e-commerce assets, such as product photos and videos. Other examples might be news and event-related content that might suddenly find new popularity. That's it for this video. Thanks for watching. We'll see you in the next video. This video covers Section 4, Part 2, Caching with CloudFront. When using CloudFront to distribute your content, you create a distribution to tell CloudFront where you want content to be delivered from. This information tells CloudFront which origin servers to get your files from and how to track and manage content delivery. Then, CloudFront uses edge servers close to your viewers to deliver that content quickly when someone wants to see or use it. You can use distributions to service many types of content over HTTP or HTTPS. For example, you can serve static and dynamic download content, such as .html, .css, .js, and image files. Another type is video on demand, which provides video content that users can watch at any time, such as Apple HTTP Live Streaming, or HLS, and Microsoft Smooth Streaming. The live event type is used to stream live events in real time, such as meetings, conferences, or concerts. For live streaming, you can create the distribution automatically by using a CloudFormation stack. When creating your distribution, you must choose the distribution type that matches your content type. CloudFront assigns a domain name to your new distribution and sends your distribution's configuration to all of its edge locations. With CloudFront, you can control the cache key for objects that are cached at CloudFront edge locations. Recall that the cache key is the unique identifier for every object in the cache. It determines whether a viewer request results in a cache hit. You can get better performance from your website or application when you have a higher cache hit ratio. A higher cache hit ratio means a higher proportion of viewer requests result in a cache hit. One way to improve your cache hit ratio is to include only the minimum necessary values in the cache key. By default, the cache key for a CloudFront distribution includes the domain name of the CloudFront distribution and the URL path of the requested object. In this example, request 2 is for the same object as request 1. However, request 2 has a different URL query string, different user agent and referrer headers, and a different cookie. But because none of these values are part of the cache key by default, this second request results in a cache hit. You can modify the cache key with cache policies. However, before you modify the cache key, it's important to understand how your application is designed. You want to know when and how it might serve different responses based on the characteristics of the viewer request. When a value in the viewer request determines the response that your origin returns, you should include that value in the cache key. If you include a value in the cache key that doesn't affect the response your origin returns, you might cache duplicate objects. That's it for this video. Thanks for watching, and see you in the next video. For Section 4, Part 3, Caching with CloudFront. To control the cache key, use a CloudFront cache policy. You attach a cache policy to one or more cache behaviors in a CloudFront distribution. A cache policy contains settings categorized as policy information, TTL settings, and cache key settings as summarized in the table. CloudFront also provides managed cache policies, so you don't need to write or maintain your own. The managed policies are optimized for specific use cases. You can control how long your files stay in a CloudFront cache before the service forwards another request to your origin. Reducing the duration means that you can serve dynamic content, and increasing duration means that users get better performance because your files are more likely to be served directly from the edge cache. A longer duration also reduces the load on your origin. Typically, CloudFront serves a file from an edge location until the cache duration you specified passes, that is, until the file expires. After it expires, the next time the edge location gets a user request for the file, CloudFront forwards the request to the origin server. In this way, the service can verify that the cache contains the latest version of the file. The response from the origin depends on whether the file has changed. If the CloudFront cache already has the latest version, the origin returns a status code 304, not modified. If the CloudFront cache doesn't have the latest version, the origin returns a status code 200 OK and the latest version of the file. Each file in the cache automatically expires after 24 hours by default, but you can change the cache duration for all files that match the same path pattern. To change the settings for minimum TTL, maximum TTL, and default TTL for a cache behavior, use the caching policy attached to the behavior. You can also change the cache duration for an individual file. To do this, configure your origin to add a cache control max age or cache control S max age directive or an expires header field to the file. To control object caching, the cache control max age directive is recommended instead of the expires header field. If you specify values for both cache control max age and expires, CloudFront uses only the value of cache control max age. You can set these parameters on Amazon S3 objects directly from the S3 console. But when using CloudFront with S3 as an origin, you would usually set caching expiration behaviors in CloudFront rather than on the S3 objects. With CloudFront in front of your S3 bucket, you can configure origin identity access, also known as OIA, to prevent objects from being exposed except through CloudFront. Therefore, you want the CloudFront caching behaviors to control expiration of S3 objects. Be sure that you don't set up conflicting behaviors in CloudFront and on S3 objects. Another way the CloudFront and Amazon S3 work together is the option to use Amazon S3 Transfer Acceleration. This bucket-level feature uses CloudFront's globally distributed edge locations to accelerate file transfers between a client and an S3 bucket over a long distance. As the data arrives at an edge location, data is routed to S3 over an optimized network path. You might want to use transfer acceleration so you can have a centralized bucket that customers can upload to from all over the world. Or maybe you want to transfer gigabytes to terabytes of data on a regular basis across continents. Perhaps you can't use all of your available bandwidth over the internet when uploading to S3. This feature incurs an additional cost. However, depending on the locations of the client and the bucket, the file transfer might not be faster with this feature turned on. In general, the farther away the client is from an S3 region, the greater the speed improvement is from using transfer acceleration. Consider this example. You'll likely see more benefit from using transfer acceleration for the user who uploads files a long distance away from the S3 bucket. The user who is uploading files closer to the bucket might not see an improvement. They might actually see slower performance than they would with transfer acceleration turned off. Test the performance on your selected buckets with access patterns that represent normal use. That's it for this video. Thanks for watching, and I'll see you in the next one.